Yeah. Hello, everyone. Thank you for joining. As Xavier Pennick just said, my talk is on a statistical phenomenon called finite sample stickiness. And I worked on that in collaboration with Dotran Van and Stefan Huckemann, who's with us today. Okay, so we have to start with a very basic concept, which maybe some of you already know. We want to take a sample from a metric space, and in order to do statistics, we need a concept of expectation. So we introduce the Fréchet mean, and yeah, the Fréchet mean is actually the minimizer of the expected squared distance to that random variable. And well, in the same way, we can define the Fréchet sample mean by taking the minimizer of the expected, of the sum of squared distances, sorry. Yeah. Okay, so this is all we need to define the modulation that was introduced by Xavier Pennick. And the modulation is actually the variance of the Fréchet sample mean times the sample size, and then we divide this by the actual variance of our distribution. Now, if you talk to people who do statistics on Euclidean cases, usually they don't care about the modulation because it is always 1 there. But this is not true for non-Euclidean spaces. And there we have some very interesting things going on, and phenomena such as smeariness, where the modulation goes to infinity, which has been described and researched by Benjamin Elsner and Stefan Huckemann. And another one, another phenomenon is stickiness. And there we have the modulation going to 0. So actually, what that means is that the Fréchet sample mean does not fluctuate, but it sticks on the point, or it may even fluctuate, but then it's like on a specific region. Okay. So my talk today is about finite sample stickiness. And this is a phenomenon where the modulation goes to 1, just like in the Euclidean space, but it is also smaller than 1. So for all sample sizes. Yeah. Okay, just to give an illustration, we have here the modulation of distributions from one space, and the black dashed line refers to the Euclidean case, and the blue line refers to the modulation of a distribution that is sticky. So you see that by a sample size of 100, it falls rapidly towards 0. And the orange line refers to a distribution that is finite sample sticky, so it falls below 1, and after some time it converges to 1. Okay. So, okay, let's introduce a definition of spaces of global non-positive curvatures. So maybe you already know this, but let's say we have a complete metric space, and we say this is an NPC space if this inequality holds. So what is the idea behind that inequality? We say that the median of a triangle should be less or equal to the Euclidean kin. So we could also talk of the angles of a triangle and say, like, okay, there should be less, or the sum of the angles should be less or equal to 180 degrees. But yeah, this is not really handy. So the median just depends on points and on the distance, and so this gives us a very nice concept of non-positive curvature. Okay, our conjecture is that if we have an MPC space, the modulation is bounded from above by 1, and in particular, the modulation is smaller than 1 if data is sampled from a negative curved region. Now, this has been shown for manifolds with constant sectional curvature, again by Xavier Penick. However, we have not yet seen the proof for NPC spaces in general. Yeah. Okay, so we come back to stickiness, finite sample stickiness, and yeah, we have stated, or that our conjecture was that the modulation is always smaller than 1 if we sample from a negative curved region, but for some distributions, due to a fast convergence of the modulation, this is not going to have an effect on statistics. So if we take a reasonable large sample size, then the modulation will be around 1 at that point, and we can just treat it like a Euclidean, like the Euclidean case. Whereas for other distributions, we have a huge impact on statistics because the modulation is below 1 even for very large sample sizes, and this is surely going to affect like statistical testing or confidence intervals or so on. Okay, so this calls for another definition of finite sample stickiness. We are not just okay with saying that the modulation should be smaller than 1. We also want to distinguish between cases where the modulation where this effect of finite sample stickiness is actually not really relevant for us, or where it has like a small effect or a large effect. So we give a new definition of finite sample stickiness. And we say, like, okay, if we have a random variable that has a non-sticky mean, so we don't want to get interfered with stickiness, then if the modulation is smaller than 1 minus rho on a sufficiently large interval, then we have finite sample stickiness of level rho. And we choose that interval by taking one integer, n, and we say like this has to hold, the inequality has to hold for all sample sizes in between n and n to the power of l, where l is another integer. So this is to make sure that the interval is large enough. Okay. Now we worked with a model space, the K-spider, and the K-spider is constructed by taking a bunch of positive real half-lines and gluing them together at 0. So we have one equivalence class that contains the 0, and we call that the origin. And then we have like, K positive reals that we call the legs of the spider. And the nice thing about this space is that it has a negative curvature on one point, that's the origin, and everywhere else it is Euclidean, so in an environment that is small enough. So this makes it possible for us to really investigate statistical phenomena that are caused by negative curvature. Okay, now we restrict ourselves to distributions that have weight on at least 3 different legs. Otherwise, yeah, we have the Euclidean case. That's like, we don't want that. Okay. So maybe to give another motivation for that space, it can be also considered as a tree space, and it coincides, for tree leg, it coincides with the BHV tree space for phylogenetic trees. So how does that work? If we have a phylogenetic tree with tree taxa, then there are like 4 tree topologies possible. And for example, we can have a direct connection between like 1 and 2, and a direct connection between 3 and 0, and internal edge in between them. So all trees with that type lay on one leg, and the length of the internal edge just corresponds to the distance of the origin, to the distance of a point to the origin. So. And the origin corresponds to the star trees where we don't have internal edges. Okay, and another concept that we need is the folding map. And the folding map is given as if you have like one eye, if we take the eye flag and we map it to the positive real half line, then we can just fold all the other legs and project them to the negative real half line. So, and this is really helpful. We will work a lot with, we worked a lot with the random variable fi of x that is defined on R, and we can just look at the folded first moments that we defined as mi, and then like the second moment sigma I square. Okay. So now it's time to come back to the modulation. We can rewrite it now using the folding map and evaluate this. And we proved in our paper that on the case spider, the modulation is indeed bounded by 1. And another thing that we know is that the modulation, if we have a non-sticky mean, then the modulation converges to 1. So this is a consequence of the central limit theory on R. But what we want are conditions for for a certain level of finite sample stickiness on the spider. So, and this is the motivation for the theorem that we introduced. That's given here. Okay. So we consider a random variable on the spider, and we consider that the Fréchet mean lies on the K flag, and that we have the second moment given, and that the third moment is also finite. Now, if the inequality 1 holds for a certain row on a sufficiently large interval, then we have finite sample stickiness. Now, if we look at the left, if we look at the left side of this inequality, we have like the sample size there, we have the first moment, the k-folded first moment, and the variance. And then we have like these two entities, Pn and Pmk, that may, they may look a bit abstract, but actually if we just go on what they depend, so we have the sample size, we have the folded first moments, the folded second moments, and the folded third moments. So, and these are just things that we can calculate for a given distribution. So, so we do know, yeah, so we have actually everything to decide whether a distribution is finite sample sticky. Okay. And yeah, I want to finish with one example that we did. So consider a random variable that is given on the tree spider, and we have like on the first two legs we have one Dirac measure at point 1 from at point with distance 1 to the origin, and at the third leg we have a Dirac measure with distance 2 plus 3 times t to the origin, and t is a parameter that we choose to be larger than 0, otherwise we are going to have stickiness. And so each point is weighted with 1/3. Then we can calculate that the third folded first moment is just given by t, and we can also calculate the second and third folded moments and apply the previous theorem. And this gives us a boundary that is shown. Oh, sorry. That is shown in the pictures at that orange dashed line. So this is just what we derived with our theorem. And the blue line refers to the simulated modulation of that distribution. Yeah, and what you can see is that if we have a higher level of finite sample stickiness, then this bound is actually sharper and almost an approximation for that modulation. But if we have a lower level of finite sample stickiness, then it is still a bound, but it seems, or the simulations indicate that actually this distribution would also hold a higher level of finite sample stickiness. Okay, so this was my talk.
Thank you very much. Are there questions in the audience? Yep.
So this plot that you got, wait a mic.
Yeah.
With the finite sample stickiness, you were showing us one of the plots where there were 3 lines. Can you go back to that one? There. So what are can you tell us what are each one of these? These are different distributions?
These are different distributions. And in fact, this is the actual modulation calculated from the example that I introduced on the last slide. And we took T large. I think the first one was just like 1, and then 0.1, and then 0.001 also. And then you see like this, the closer we get to the origin, where we have negative curvature, the more, the higher the level of finite sample stickiness.
Okay, thank you.
I just wanted to ask, can you give just a quick intuition of why you have, when this behavior when t turns to 0, that you have stickiness? on the example that you have, why is there this choice of like, I don't remember, 3 plus t or something like this?
Why we constructed that example in that
like,
way?
Okay, can you just give the intuition why you have stickiness when t turns to 0?
Okay, so what I couldn't discuss in detail, but you can find this in the literature, and it was in fact proven, I think, like 2013 or so, that if we are at, or if the Fréchet sample mean is at the origin, no, sorry, if the Fréchet mean is at the origin, then we have stickiness. So, and what is happening now if t goes to 0 is that the Fréchet mean is getting closer to the origin where it becomes sticky. So it's just, we have this is the sole point with negative curvature, and this effect of negative, or this negative curvature affects our distribution. The stronger, the closer we get to the origin, the closer we get there. I don't know, was that helpful?
Yeah, just one very quick answer if you have one. But it seems that, so in your definition, so you're trying to measure what is the dip of the modulation, but then you're going to 1 in the definition, and it seems to me that this is so this is going to 1 because basically when the Fréchet mean concentrates, then it goes in a flat part of the space, which is one of the legs.
Yeah.
So, do you think you could adapt the definition for the case where it's actually the modulation does not go to 1 but to something lower? Because if you're concentrating on in a stratified space on a part where you have negative curvature, then you're not going to have something that goes to 1, but something that goes to something below 1. But you could still have this effect that with low number of samples you can still feel the singularity, but with higher number of samples you're concentrating out of the singularity.
I think, yeah, this should be possible by so that was it. So if we have like or if we know that the modulation does not converge to 1 but to a lower level, that we adapt, or we take 1 out here and
Okay.
adapt it.
So we should still see the same behavior with this type of stratification.
I'd assume, yeah.
Okay.
If we have